Thank you very much, Richard. Good morning, everyone. Thank you for inviting ICARDA and our presentation to your online meeting. I wish you all a pleasant morning and hope you will enjoy a presentation from the very dry corner of the world from Jordan. It's about obtaining agro-hydrological datasets in the marginal drylands of Jordan and the two-sided lessons learned and shared between the scientists and the farmers. It's an ongoing activity, and it's like a project or several projects from ICARDA with its national partners, including NARS, the National Agriculture Research Center, but also plenty of universities. And this is where the topic is about young students doing their master thesis and exchange in this work and in interrelation with the local farmers and agro-pastoralists. To give a short background about the story, Jordan is among the most water-scarce country, always listed among the top 10, top 5, or even worse, of water availability per capita. And if you look on Jordan, the areal extent, around 90% of the territory receives less than a 200 millimeter of average annual rainfall. So 90% of Jordan is arid and is, let's say, tribal, ex-Bedouin tribal area where agro-pastoralists were circling around and feeding their livestock in the dry rangelands. But meanwhile, because of changes in the management, because of shifting to sedentary practices, but also because of demographic changes, migration, unrest in the area, the ecosystem services, the biomass was over-facilitated, water was over-facilitated, land started to degrade and speed up the cycle of degradation. So actually, the soil is depleted, vegetation cover is gone, and water quickly just leaves the watersheds. So it looks like there is no water at all, but in fact, there is water in Jordan. Every year something like this happens. I mean, I don't want to say something wrong, probably not every year, but very frequently the cities get flooded. So obviously there is water just at the wrong place. So ICARDA with its partners, NARS and also in international organizations, we started to frame a rehabilitation package, which means the breaking up of the degradation cycles through micro-water harvesting, mechanized, outplantation of native seedlings and shrub species, and trying to allow nature to build itself, to strengthen itself and to come back to a kind of resilient status. So actually what we do is we mimic the nature of retaining some water in the watershed, locally infiltrating it and boosting shrub growth, vegetation growth, and to come back to a sustainable rangeland habitat which feeds the agro-pastoral agriculture sector. So just to show the process, how it looks like, this is directly after implementation of the degraded lands of the micro-water harvesting. Water from the interspace gets intercepted, locally infiltrated, which boosts the shrub growth. Certainly also some water passes over because we don't want to save all the water. There is a downstream as well. And also sediments and seed material get stored in this kind of pockets to thrive also, let's say, the seed material, which is still stored in the soil. So in the end, water gets harvested, water gets locally infiltrated, and this gives a chance for nature to come back. So our hypothesis behind is that we know, based on desert castle paintings, based on stories, based also on some protected areas, there are some semi-beneficial productive drylands. They were degraded to the lower left corner, and our breaking up the cycle approach would move it back. And we want to understand how this kind of ecosystem transition goes along, what are the implications, and where does then the equilibrium reach? Like, does this rehabilitation approach come to an equilibrium between water, sediment, yield, degradation, and deposition? So this is an example of how it was last year, actually, after 2.5 years of the implementation. You see the left side is the restored watershed, the right side is actually at the peak of barley seeding, of degrading the soil On the right side, this is the emergence of the agro-pastoralists by doing barley agriculture, but it's still very, very dry. And the left side, you see there is some biomass back, some shrub system, some kind of rangelands coming to emerge. So this is the theoretical response curve we have in mind. Like after you break up the cycle, after you do this water harvesting intervention, you have a high retention volume, which keeps a lot of water. But degradation over time, siltation of this pit, erosion of the water harvesting rim will lead to, let's say, a microtopography at the long term. At the same time, vegetation comes up and vegetation takes part of the job. In the end, it should do all the job. So vegetation should intercept rainfall, should decelerate the runoff, should break up the crusted surface and allow infiltration. So this is the hypothesis, but we don't yet fully know and understand where it goes. And there it's very important to start with some science, but at the same time to break the science down to some understandable messages. So we want to understand what happens, and we want to frame it to some kind of share resources for decision makers, but also for the local people. So at the end, we have scientific approaches, advanced monitoring, advanced experiments, GIS, computing. At the same time, we have some robust experiments in the field. We want to merge the local knowledge with the scientific message and to bring it also to some standard. For sure, it should be publishable, and to choose a common language without being too much hydrologist. What we choose in this concrete example is we tried to make science products out of it, and one student, he's actually co-author of this presentation, Joren, I think he joined, he framed it for a WOCAT entry, so our rehabilitation approach for WOCAT, to store it there and to disseminate knowledge on this well-established platform. So you have now the two sides. You have on one side, let's say, the more scientific approach, for example, burying soil moisture sensors, which sends the data to a cloud or to a server. At the right side, you see local people, farmers, taking the response for the shrubs, for the vegetation. There, we need people going there and measuring. No remote sensing product will do this work for us. So that's why we have to merge this kind of two approaches. And you see the techie part and probably the robust part, but in the end, it looks very much the same. It's probably looks like a joint work. This is, I don't want to go too much to detail, but just to show you some data examples. On the left-hand side, you see soil moisture response time series of degraded rangelands in orange, of restored rangelands in blue, how much more soil moisture response you have over time. And on the right hand, you see the vegetation response, how the vegetation, let's say, starts to develop. Without going too much into detail, but you see it looks, let's say, similar, but the point is the right data was collected by the farmers, the left data was collected by the students, and in the end, they are harmonized and they are brought together and they explain each other. So for example, the vegetation response gives us knowledge why and what certain water does in certain time and space. So it tells us the complete story. We would only harvest numbers, soil moisture values, which itself don't make much sense because the product, the decision maker or the farmer is interested in biomass. So that's why the farmer take the biomass, but we try to understand the process and we meet each other somewhere in the middle. So probably everything what I said is here. We have remote science approaches, let's say the students or the international scientists' work versus the local and robust approaches. These two meet together because these highly detailed processes from the remote or the high-techy approaches, they not necessarily make sense. Often the values do not directly make sense. Soil moisture values don't tell us, does the plant grow? Is the plant stressed? What kind of biomass will it yield to? So it needs both, and we also need, let's say, from the local farmers, we need the backup, we need the description of the process. We need also the buy-in, and that's why working together is so much important for us. So one concrete example, for example, when we show on microtopography, when you look on harvesting potential, which is part of the figure I showed before, you can go with the close range photogrammetry or whatever to analyze the capturing volume of the structure. This is probably the science part, but the reality, the process is different. This is what happens in nature. We have recruitment of shrubs. We have residues which harvest some part of the water before it even comes to the microwater harvesting pit and infiltrates water before it even enters the pit. We have management, and this is what we want, facilitations through animals. They in the end trample down the water harvesting structure. So in the end, we need to link the things together to get an idea about our hypothesis. If this kind of water harvesting structure declines over time, what kind of local processes, what kind of speed, when can we expect certain equilibrium status? So we are on the way to stage 2, but we are still on the way and we still work with our local communities. And just to say, for example, in this moment in Corona situation, the local community stays in contact with us with the WhatsApp group and updates us. They look on processes which occur just in a moment, like a dust storm. This picture was taken by a local guard, by someone who takes the hydrological measurements. He just took the picture and told us this and that happens. If we cannot enter the site, or if we cannot explain processes, for example, this is a picture from just 2 months ago in the lower left corner. This is hail. So water comes in hail and ice, and we don't understand the response time from precipitation to runoff. But these pictures and the groups and our local partners explain why certain process changed. And at the same time, they facilitate, they manage the land, and they stay in contact and update us on what happens. So eventually this helps us to come up with quite complex models for outscaling. Just to show you, we link different on-site data with modeling to come in the end to a product which helps us to assess ex-ante outscaling to other areas not yet approached. At the same time, by our science products, so the science products we deliver, let's say for science publication, also for ex-ante assessment, for probably narrowing the message down for decision makers, but at the same time, we need to fill in the information, let's say digestible for decision makers, which is the right side. You see the WOCAT entry. Our student did this. He went to the field, he assessed on the site, he made expert questionnaires and tried to bring this techie data into something understandable in some sheets for decision makers. And at the same time, we also raise awareness from the local people. They know the process behind, but sometimes they under-consider the importance of what they do and probably sometimes even the linkages. So at the same time, we try to break it down. The lower left corner you see this was a play, like a theater play, which a social scientist did. She made a nice choreography with the students in the school and made a play around sustainable facilitation of assets in the rangelands. That's how we try to get knowledge from these people, but at the same time to share and feedback what we find to raise also the local awareness. In the end, it might look like the techie part is done by the students and the robust part is done by the farmers, but that's not always the case. Here you see a picture of partially ICARDA, partially students, and partially local farmers. And just as an example, also the local farmers helped us with time domain reflectometry, soil moisture sensing. So in the end, also this capacity was enhanced. At the end, the lessons learned and shared was to better understand each other. For example, local students or international students which come to the site start to understand local processes, start to understand uncertainty and reliability of data, and framing the right research questions. The value of scenario point is many times we get students, for example, from the Netherlands, quite advanced students when it comes to modeling, remote sensing. And then when it comes to modeling in our data scarce area, the first question always coming, we don't have validation and calibration data. And then is when we go back to the Bedouins and ask them, from the last 40 years or 30 years, how many times per year in average is this area flooded? How many times this and that happens? So that's where we try to find the local knowledge as the right verification and calibration data. And then people start to understand that modeling and ex-ante assessment is especially for this, to assess areas which there is no data yet or no time series. And then to link the short-term high-techy part with the process and the long-term memory. At the same time, the local partners, they sometimes need to be reminded about their local knowledge they have. So sometimes they are not that much aware about it. And the awareness of the processes of slow infiltration is related with land degradation. Many times people come to us and say, okay, what can we do? I saw in this experiment, it took 2 days for water to infiltrate. What's the problem? So it raises really the kind of awareness, but at the same time, it's capacity development on technologies, on administration, and also on communication and the openness to exchange with students and science. And by creating this openness for exchange, also opening the willingness to change the behavior to also allow the sustainable management of what we achieve together. Yeah, that was in a nutshell about this project. Thank you very much. And I think I used my time already. So thank you, Richard.